Yeah, hi and welcome everyone to my talk here. I'm M.Beckers, as it was said before. Okay, and I'm working in the job shop and testing facilities department at Connect3D. And today I'm going to talk about the influence of different laser beam intensity profiles on the process and part properties in laser powder bed fusion. I want to start with a brief introduction of our company, followed by the experiments and results in the short summary afterwards. Yeah, Connect3D is a laser powder bed fusion machine manufacturer located near Aachen in the most western part of Germany. And our mission is to accompany our customers on their way to additive manufacturing and especially laser powder bed fusion. Starting with the basic or advanced consulting, we identify the customer needs. And then in the job shop, we run some feasibility studies, some process developments or small series productions, just to get the right machine to the customer. And as broad as the variety of the customer needs is, no machine is rarely the same for different customers. So the majority from our staff came from Fraunhofer IoT, and working at IoT very soon was clear that to develop an advanced process, the full access of hard and software components is needed. And that is the main motivation why Connect3D was founded. And starting with our four different bases of machines, our customers can configure their machines on their own by choosing different laser sources, different process monitoring systems, as well as separate chambers or heating modules from 500 degrees up to 1000 degrees and more. But this flexibility is not just present in our hardware, but also in our software. Our Connect Studio is the heart of the machine, which enables the operator just not only to print parts with the standard parameters given by the manufacturer, but also to develop their own expert parameters and processes. But looking more on the process side of view, I think everybody knows that LPBF is a quite complex process, and that there are interactions of various physical phenomena like absorption, heat conduction, or even evaporation, leading to a highly dynamic temperature field, evolving certain volume of molten material that solidifies again afterwards. And these many influencing factors are not fully understood yet, but as a machine manufacturer and operators alike, it's our passion and our daily bread to ever better understand this chaos and to influence these process parameters in our favor. One way to influence this process is the different laser beam sources, and for that, Enlight developed the AFX 1.2 kilowatt laser with 7 different intensity distributions. This is standard Gaussian one on the left side, up to the ring beam on the right side, and 5 more different intensity distributions in between, differing in the power ratio of center and ring, so that it's possible to print filigree parts, mixed geometries, as well as bulk parts for productivity reasons, for example. And one important thing is that you do not need any additional setup to shape your beam, but you can switch the beam profiles within millisecond timescale on the fly within the process. And to investigate this laser, we ran a time-consuming and broad parameter study with index 0, so the Gaussian one, index 6, the ring beam, and index 3 is the hybrid one, with hundreds of cubes for the nickel-based Super LR718. And one important thing was for us that we kept the processing conditions absolutely constant. So the inclination angle of the laser, that means the position on the substrate plate, as well as the shielding gas flow, and etc. And in this context, we defocused our spot diameter from the index 0, so the Gaussian one, to the outer diameter of index 3 and index 6. At the first result, what we could derive were some processing windows and classified by processability and densities over 99.5. Please note that this is just an extract and not an absolute statement of the processability of nickel-based Super LR718. But however, what we can see at the first result that the process stability increased with the ring mode intensity distribution, probably due to less intensity peaks and less overheating. Yeah, they were the starting point then for further selection of suitable parameters to be analyzed afterwards more in detail. But in the meantime, we thought of a more straightforward way to qualify a good process. And what always occurs in LPBF is spatter formation. And what you can see here is the same geometry printed by index 0 and index 6. This spatter formation can affect your process in two ways. By insufficient melting of a big particle which lands on the not yet exposed area, or by affecting the roughness of your part afterwards. And this helps us now a lot because we do not have to wait for hundreds of cubes to be printed or analyzed, but the well-trained operator then could run a variety of different processing parameters within a process and can change the process parameters on the fly. That helps us a lot this way. But just as an excursus and coming back to our conventional analysis and parameter study, already the mechanical properties revealed some big differences, while we have some comparable or slightly higher yield strength for index 3 and index 6. The elongation at break was much higher for the samples of index 3 and index 6. And that was clear that we have to dive deeper into our analysis and to better understand the underlying mechanisms. And for that, we had a look at the microstructure at a coarse microscopic scale, light optical microscope of edge cross sections, as well as the SEM image analysis of primary dendrite arm spacing and the segregation behavior. Didn't reveal any big significant differences, so the primary dendrite arm spacing was almost the same. And that got supported by another thermography video. So what we tried is to detect some cooling rates, and therefore we had a fixed look at one point in the area to be exposed here on the left side. And while the laser spot passes by this spot, we could detect some heating and cooling behavior of the material for any index, but even at sufficiently high temporal and spatial resolution of the thermography camera, we still face the challenge that the emitted radiation, which we detected, got affected by phase changes, the surroundings, or everything which is flying through the picture. However, the comparison of the data generated by thermography and our parameter processing monitoring operating at 100 kilohertz even is a thing we are currently working on. And it's the potential benefit of this approach encourages us to keep on working in that direction, but there is still work in progress. One thing we then analyzed was the XY micrographs, and what we can see here is that on the left side, on the bottom, for index 0 samples, the grains are a little bit elongated in XY direction, whereas almost every grain here is kind of equiaxed for index 0 sample. And that was the first indication for a preferred direction of grain growth for us. So we dive deeper into the texture analysis via EBSD. And what you can see here on the left side is that the grain orientation for the sample of index 0 is quite irregular, while it is strong, and sharp, strongly preferential orientation along 0, 0, 1 for the samples of index 3 and index 6. But then naturally the question came up, why is that pronounced for the different intensity distributions? And our explanatory approach was to have a deeper look at the dendrite growth, because it always occurs on the shortest way from the coolest to the hottest point, so in a 90-degree angle from the melt pool boundary to the center. And indeed, the melt pool shapes were different, deep and not that wide for samples of index 0. Whereas the melt pool shape for index 3 and index 6 was much wider and flatter, leading to less competitive growth of dendrites for those samples, which leads to a strong epitextural growth over many layers, so that we get a sharp texture. And then we asked the question if it's just only possible for this aspect condition or this orientation? And the answer is no. We did some further experiments in the heat-treated state, and even in the heat-treated state, we could see this trend or this phenomenon of a slightly higher tensile or yield strength, while the elongation and break was much higher for index 3 and index 6 samples. And even at higher testing temperatures, we could see this trend here for 650 degree C tested tensile specimen. Yeah, what we then thought, is it only possible for simple geometries, or is it even possible with realistic components? And as you can see here, it is. We printed the turbine blade out of this nickel-based superalloy and ran another EBSD analysis. And what we did is to print at different heights, different indices. So index 0 on the bottom, index 3 in the middle, and index 6 on the top. And those trends were, confirmed here again. So it's reproducible, and the irregular oriented grains here for index 0, whereas the texture is really sharp for the sample of index 6 and the area on the other side. That got supported by the grain boundary analysis. So we can see here, kind of equiax, so to say, grains in the Z direction for index 0 sample, whereas they are much more elongated for index 6 samples. So we could, by differing the different intensity distributions on the fly, we could influence the growth of the crystals within the process. And coming to an end, I hope I was able to convey you that LPBF in general is a process with a huge potential to not just simply print parts, but also to adjust your microstructure or your part in a micro and macroscopic scale. And we are just at the beginning of exploiting these capabilities. Thank you.